All right, welcome back, everybody. We're going to continue our foray into orthogonal bases with a bit of a conundrum here. There's always this question of existence and possibly uniqueness in math. So you'll see this in differential equations all the time, asking if a solution exists, then is it the only one? Or going even further, is there even a solution at all? Well, yeah, we're going to find something similar in our scenario here. What we really want to ask is, does an arbitrary inner product space possess an orthogonal basis? Right, we would really like to answer this question. Is it even possible to construct something, right? We don't want to have to go through we don't want to start an algorithm if we are not 100% certain that this thing is going to terminate or it's going to find a solution to the problem. So you don't want to start looking for a solution that doesn't exist, right? So does an arbitrary inner product space possess an orthogonal basis? And for right now, we assume that the inner product space is finite dimensional. The question so the question becomes a little trickier in infinite dimensions because the idea of a basis is a little trickier to deal with there. But what we're going to do in this video is show that actually, yes, the answer is yes. You can find an orthogonal basis for any vector space or any inner product space specifically. But it stems from the fact it needs a basis to begin with, right? So this goes back to something like Zorn's lemma, right? Begin with, right? So in some sense, this basis that we start with is going to be the seed of an algorithm that will kind of germinate into this, or that will blossom into this orthogonal basis, right? We're going to modify an existing basis to turn it into an orthogonal one. And this is the idea behind the Gram-Schmidt process. And we're going to try to outline it as best as we can intuitively here before we state the actual theorem behind how we know that every inner product space has an orthogonal basis. So we'll come to this question then. How can we take an existing basis and make it orthogonal, right? And what we have here, let me see if I highlight these guys in blue, right? So the two vectors that I have listed in the beta set here, right? These guys are already a basis of R2, and R2 with the standard inner product is what that notation is, right? So we would like to be able to take this basis and kind of pull the vectors around in such a way that they are not too far from where they started, right? We're not modifying the set too much, and yet we are still creating an orthogonal set at the end of the day. And this is where we're going in this picture. We're trying to say that we like V1 the way it is. But what we have to do here in order for us to get to V2, we would like to take a perpendicular, right, an orthogonal projection of this vector, V2, onto this line that is spanned by V1. We want to see how much of V2 lives in that line. And that's what this x vector is doing. It's telling us how much of V2 is in this V1 line. Okay? So we can see if we have x and y vectors here, that V2 is just going to be the sum of those two vectors, and x and y are going to be orthogonal to one another. And this is what we want. We would like to replace the V1, V2 basis with the xy basis. So in particular, we would like to show how much of V1 is in the V2 vector. So that's where this first part of the argument is going. We're trying to see what that shadow of V2 looks like on the span of V1. Right? So let's not modify V1. Let's keep the set beta as close to the original set as we can. So we'll keep our new set of vectors as close to the original as we can. So what we wind up doing is saying, let's just go ahead and say that the first vector in our new orthogonal set is going to just be the first vector of the original set. So just go ahead and set u1 equal to v1. Done. That's step one. Second, we need to know how to modify v2 so that it is perpendicular or orthogonal to v1. All right. So how are we going to do that? Well, let's replace v2 by u2. And u2 needs to be something that is orthogonal to u1. But we know this relationship here, that x plus y, right? So in this case, x is equal to some multiplicative constant times u1. But in particular, what's happening here, we are saying that v2 is going to be some amount of v1, which is u1 in this case, plus some amount of u2. Okay? And that's not too hard to show, actually, because we already know that if u1 and u2 are an orthogonal set, so let S be u1 and u2, then the theorem from last time, right, our coordinate theorem, tells us exactly what the coordinates of v2 have to be. Right? We know exactly what that has to look like because we have an orthogonal basis or an orthogonal set. So that would mean that v2 here, and I didn't put that on there, there should be a u1 right there. There we go. Then v2 times, v2 time or minus this quantity. So if I solve for this here, then we are looking at this quantity here, this difference of vectors, v2 minus this multiple of u1. What you think of it as v2 minus this x vector, the thing that's left over has to be this other side of the right triangle, the other leg. Right? So this is in some sense acting like the y vector in that picture. That the difference vector is some multiple of a vector that we want, something that is orthogonal to u1. Right? And that's what we're going for. We're trying to figure out how to create a multiple of the correct thing. And this we can actually double check, right? Or we can actually use our example set here, right? Our set was up here, 1, 1, and 3, 1 are the two vectors involved. We're going to go ahead and take u1 equal to 1, 1, right? We're going to keep this guy the same as v1, right? And then to construct u2, right, we're going to have to take the difference vector here that we just computed above. That v2 has to subtract off some proper multiple, the exact right multiple of u1 in order to produce something that is orthogonal to it, or not orthogonal to u1. Right? And that multiple is exactly this quantity that we get from the orthogonal coordinates theorem. All right. So we can compute all of these dot products. So v2 with u1 here, this is 3 by 1 dotted with 1, 1. So sure enough, that's a 4. And the length of u1 squared, so u1 squared, this is just u1 dotted with u1, and that is 1, 1 dot 1, 1. And sure enough, that's a 2. So the 4 goes right here, the 2 goes right there, and Bob's your uncle, Fanny's your aunt. That's how much of the u1 vector we have to shave off of v2 in order to produce something that is orthogonal to u1. And that little bit of algebra at the end there, you notice u1 dot with u2 is exactly 1, 1 dotted with 1 minus 1. And they are automatically orthogonal. Magic? No. Math? Yes. All right. So this is the idea. We are shaving off, or we're modifying the existing basis in such a way that we are producing vectors that are orthogonal to what's already in the set. So, oh hey, look, I do the check on the next page. So we double check. This is an orthogonal set, right? And if we want this to be orthonormal, we really only have to do one more step. We've seen that. We just have to divide by the lengths of each of these vectors, and sure enough, these guys are now going to be an orthonormal set. And in fact, they will be an orthonormal basis for R2. So the takeaway here is that we can just normalize the vectors at the end of the process, right? So this is going to save us a lot of computational heartache as we employ this algorithm for more vectors, like a higher number of vectors. Okay, so again, it's this computation in the middle here is just to show you that you wind up with the same thing at the end, which you're just going to go ahead and scale to whatever you want it to be anyway. So you might as well just do your scaling at the end of the process rather than along the way. There is a computational advantage to doing it along the way, and we will see an issue with this. We're going to be talking about the stability, the numerical stability of this algorithm soon. But for right now, when you're doing this by hand, save yourself some trouble and just normalize at the end. Normalize at the end of the process. Okay? So if you want an orthonormal basis, just do it at the end. But let's say we bump up the complexity here. Let's say that we're trying to do this for 3 vectors now. This is an arbitrary basis of an inner product space that we call V, right? And this is going to become, this basis is going to start off the same way. We're going to go ahead and say let U1 be V1. And we're going to use our orthogonal coordinates theorem to say that V2 is going to be some amount of U1 plus some amount of U2, right? And we know that these weights here, the theorem says that this is going to be V2 against U1 divided by the length of U1 squared times U1 plus V2 with U2 over the length of U2 squared U2, okay? Which means that the vector I want here, this thing, this U2 multiple, right, I want this, but I only know those two, these two quantities, 1 and 2, right? So what I have to do here is take the difference. So this would imply that V2 minus V2 U1, sorry if you can hear the leaf blower in the background, they schedule at the most inopportune times. Seems I can't escape this, either on campus or off. There's always some leaf blower outside my classroom. But this is going to be effectively the y vector from before, right? So this will be a multiple of the correct vector, and I don't care what multiple I get. I just need some vector that is orthogonal to U1, and this will get it for me. No problem. Okay? Yeah, they are relentless outside with the leaf blowers. They've been going, like, I've got 108 on my tablet right now. They've been going since like 8 or 8:30 this morning, and they are still going. But anyway, I digress. This is the vector that we choose for U2. This is going to be orthogonal to U1. And you can even check it. U1, inner product U2 here. Well, this is going to be U1, inner product V minus V2 U1 over U1 squared times U1. We go ahead and distribute, so this is U1 with V2 minus, well, I can go ahead and pull out that multiple, so V2 with V1 over U1 squared, and this will be V2, is that right? No, it's U1 with U1. Right, U1 with U1. Oh, shoot. So notice, this is U1 V2 minus, well, these two guys cancel each other out. So I'm just left with V2 with U1. And sure enough, that's 0. So the thing we just constructed is indeed orthogonal to U1. Okay, and we can play this game ad infinitum, right? So we are going to do the same thing. We're going to say that V3, the third vector of our set here, is going to be some combination of U1, U2, and now this third vector, U3, that is orthogonal to both U1 and U2. Right? And in general, this is exactly our theorem. I goes 1 to 3, Ci, and it'll be V3 of Ui over the length of Ui squared times Ui. Okay? But really, we just want the last component here. So I'm going to sum this out to 2, and then I'll have C3 times U3. And this is the vector I want. So what I have to do is shave off those components, right? I have to shave off the amount of V3 that lives in U1 and the amount of V3 that lives in U2, or the other way around. The amount of U1 that lives in V3 and the amount of U2 that lives in V3. So the result here is that I wind up with a vector that I'm going to call a U3. It's going to be this third vector that is orthogonal to everything else that came before it. All right? And that's the whole point. We are building up this basis, this orthogonal basis, one element at a time to create an orthogonal basis. Okay, so we're modifying this B, or this beta vector, or beta basis, which is already linearly independent, right? Or it's a basis, or it's just some linearly independent set. It doesn't necessarily have to be a basis, but this is a linearly independent set. We are going to define our starting point, U1 equals V1, and we're going to build the UKs in exactly the same way. We're going to shave off the appropriate amount of all the vectors that came before it to produce something that is orthogonal to everything that came before it. Okay? So U4, for instance, would be orthogonal to U1, U2, and U3 in this algorithm. And then we're going to have to create U5 by shaving off pieces of U1 through U4. Okay, so just as an example. Okay, and in general, what this does for us is it creates an orthogonal set that still spans the same thing that the original basis did. So these guys, if we start with a linearly independent set, beta, then that is a basis for the span of beta. And what we're saying is that we're replacing this basis for beta with an orthogonal basis, gamma, for the same span. And this process, right, this idea of shaving off the appropriate amounts, the right weights at the right times, this algorithm right here, right, this guy is known as the Gram-Schmidt orthogonalization algorithm, or Gram-Schmidt process, if you will. All right. Let's go ahead and kill this video because that's just the setup. Let's save